This lecture is going to cover the concept known as the central limit theorem. And in order to talk about the central limit theorem, let's think back to the stuff we've done over the last couple lectures. What we've been doing is we've been given some distribution and we knew that it was normal. We knew the population mean and we knew the population standard deviation. But in the real world, knowing things about your population is very unrealistic. The only way you would know something about your population for sure is if you had every single observation. And most of the time, it's unlikely to have every single observation in a population. So a lot of the stuff that we have been doing hasn't really been that realistic. We've been given a mean, given a standard deviation, and we're told that it's normal. So what was the point of all that? Well, let's take a look at something called the central limit theorem. Here we have that web page of the sampling distribution, and I'm going to hit begin at the top left here. And if we remember, when we have a normal distribution, and when we take, let's say, 5 observations and plot the mean, that too becomes normal, right? And if we were to repeat this process over and over again, we saw that this becomes a normal distribution. You have an original normal distribution, the distribution of the sample means becomes normal. And on top of that, we have these same exact means. The only thing that changes is your spread. However, you don't always have a normal distribution. What if we had a skewed distribution? We've talked about skewed distributions. We've seen data that's skewed. Well, what if we were to do the same process? We have a skewed distribution. Let's take a random sample of 5 observations and plot the mean. Random sample of 5 observations and plot the mean. We can do this over and over and over again. 5 observations, plot the mean. And what we'll notice is if we simulate this over and over and over again, this new distribution of sample means, while it's not perfectly bell-shaped, it's a lot less skewed than it was before. Right? On top of that, what we'll notice is the mean of our original distribution is 8.08. The mean of the distribution of sample means is also 8.08. They have the same exact center, but the shape is different. Watch now if we do this with 25 observations. Right, we're going to take a sample of 25 observations, and from that sample, we're going to plot the mean. And we can do this process over and over and over again, right? Simulate this process over and over again. And now when we look at this distribution, lo and behold, look how much less skewed that is. In fact, it barely skewed at all. What happens is your distribution will get closer and closer and closer to a normal distribution. The more observations you have in your mean, the closer your distribution of sample means of that size will become a normal distribution. This is the big magic trick of this class. And this is called the central limit theorem. It didn't matter that we didn't have a normal distribution. If you take enough observations and plot the mean and repeat that process over and over again, your distribution will eventually approach a normal distribution. But that was just skewed with a skewed distribution, right? What if we have some funky distribution? I'm going to kind of make my own distribution. I'll dance a little bit with these bars and bins. Let's say something like this seems cool. Right? And in the first graph we'll see, I'm going to plot the mean of 5 observations, and the lower one, I'm going to do the same thing for 25. So I'll animate this process. We now have this funky dunky distribution. And the lower graph is going to give us the mean of 25 observations. And so we can repeat this process, plot the mean, right, over and over and over again, repeat this process over and over and over again. And what we'll find is your distribution, even though it started from this funky dunky distribution, this crazy distribution, the distribution of your sample means will become more and more normal the more observations you have. And on top of that, your spread will shrink the more observations you have. And what you'll see here is for every single graph we have, the mean 15.41, the mean 15.41, 15.41. We have the same exact center in terms of the mean. So it's going to be important for us to remember these things. We don't have to have a normal distribution for the distribution of sample means to be normal. What we need to have is a large enough sample size in order for these distributions to be normal, the distributions of sample means. Because, for instance, if we only had a sample of size 2 and we did this process over and over and over again, right, your distribution with only 2 observations is not normal. So we need to take enough observations in order for the distribution of sample means to be normal. This is the central limit theorem. This is one of the natural phenomena that exist in our world. And to be honest, if these distributions didn't become normal, we may not be taking the statistics class right now. A lot of stats, especially when stats started out, has to do and deal with this concept of the central limit theorem, that these distributions, these sampling distributions, approach a normal distribution. The central limit theorem, by definition, essentially says, hey, regardless of what your distribution is, regardless of what the shape of X is, if you take enough observations, the distribution of your sample means, or what we'll see shortly, the distribution of your sample proportions, becomes approximately normal. And we'll talk about, well, what sample size do we need in order for us to have a sufficiently large enough sample size for the central limit theorem to hold. Now, we talked about this in the simulation, but just so you have these in your notes, the sampling distribution of a mean or a proportion will become approximately normal. It didn't matter what the shape was. We also saw that the population mean of a sampling distribution will have the same exact mean from the original population, or proportion, which we'll see in another lecture video. On top of that, the population standard deviation of our sampling distribution, which we call the standard error, the more observations we have, the smaller spread we get. Now here we're looking at a picture of what we witnessed through simulation, where we have different shape distributions, and we can see, depending on the shape, is going to affect how many observations we need in order for it to be normal. Here we kind of have a skew distribution, and our sample size is 2, and we can see our distribution is still not normal. When we have this weird hump distribution, bimodal, our distribution is not normal. When we have a uniform distribution, not normal. If our sample size comprised of 10 observations, the means of that size become somewhat normal for a uniform and for a bimodal, but they're still skewed in a skew distribution. It seems like when we take 30 observations, all of these shapes follow a normal distribution. So why is this so important? Why is it important to know that the distribution of your sample means is normal? Here's why. Because what happens is we don't really know the population shape. Maybe it's bimodal, maybe it's skewed. If so, how skewed? Maybe it's bell-shaped, but is it normal exactly? We don't really know the shape of our distribution. What we do know is that if we take enough observations, the distribution will eventually become normal. And we know how to calculate probabilities and percentages with a normal distribution. We don't know how to calculate probabilities and percentages in a funky distribution. Let me show you what I mean by that. Here we have a distribution that's some funky shape. Again, not everything follows that perfect bell shape. Some stuff is really weird, right? This distribution has a population mean, which we never really know. But what we can do is this. We can take a bunch of observations. And from all those observations, what we can do is we can find and calculate a sample mean. And then down below, we would make a graph and we would dot that sample mean. And we can repeat this process over and over again. Take another sample, plot the sample mean. Another sample, plot the sample mean. And just keep doing this process over and over again. What we found is if our sample size is large enough, again, we haven't talked about that size. If our sample size is large enough, the distribution of those sample means becomes normal. And on top of that, the mean of this distribution is the same exact value as the original distribution's mean. These two values are exactly the same. They have the same center. And so what we're going to be able to do is this. We're going to be able to calculate probabilities and percentages in this normal distribution. We know how to calculate probabilities and percentages in this normal distribution. We don't know how to do that with our original distribution. We don't know probabilities and percentages in our original distribution. We're going to be able to estimate this population mean. We'll use a sample of data to try to estimate the mean of our sample means, this black line. We'll try to estimate this. And the reason we can estimate this is because we know how to calculate percentages in a normal distribution. We'll learn some information about the mean of this distribution. And what happens is, since these values are the same, if we learn about this mean, we'll be able to make an inference on what that mean is. This is why the central limit theorem is so important, because we're going to be using a different distribution to estimate the parameters of our population that we're interested in. What we need to think about now is, how are we going to estimate those things? How are we going to estimate our parameters? Throughout the course, we're going to use two different techniques to estimate population parameters. One of which is called a confidence interval, and the other is called a hypothesis test. Both of these are ways in which we can learn something about a population. We can learn something about a parameter that we may be interested in. And we'll talk about the similarities and the differences between these two methods.